All right, it's 1 o'clock. I think we're going to start. Good afternoon, everybody. My name is Boris Bereshnikov, and together with me, Connor Cunningham today. And today we're going to talk about query performance troubleshooting. So what we're hoping that you will learn in this session today is that how the query processor team, meaning us, in particular in this case, approaching debugging troubleshooting, various troubleshooting issues when they come to us. And there's few ways and few techniques we're going to show you on examples how you're going to approach the system slow or particular query slow troubleshooting scenarios. And we are going to focus primarily on the query processing, on the query processing related causes for those problems. And we're going to show you quite a few examples, and I think that's where the essence of the talk is. A few examples of how you're going to see what tools you can use, how you can understand. All right. I'll try to speak up a little bit. We're missing the AV person. I think he can bring up the volume. I'm going to speak into the microphone. Is it any better? Okay, good. All right. I will try to maintain the constant distance between Mike and myself, so that will alleviate the volume problem. So we're going to talk about tools, methodology, what to look for, and most importantly, we're going to give you we're going to give you information about how the system works, so you can actually better understand why the system behaves in a certain way, so you can actually better troubleshoot it. So there are enough books, enough white papers, enough information on the web where you can just do prescriptive guidance. You can run tools and look at the numbers and determine what the problem is. We're trying to give you information of how the system works itself so that you can better understand why you're looking at the particular problem or why you got in this particular problem in the first place. And before we continue, a couple of words about ourselves. So I've been with Microsoft for the last 6 years, and I was always in SQL Server Engine. I worked on a variety of features, but among the big ones I worked on, I built resource governor in SQL Server 2008. So this is a fair questions if you want to ask at the end of the talk. And currently I'm working on a few features related to perf troubleshooting and the predictability of query plans in general. And I'm sure many of you have heard the talk of David DeWitt in the morning, so we should have required as a prerequisite for this talk. So Connor.
Hello, everyone. For those of you who didn't attend my talk yesterday, I'm Connor Cunningham. I work with Boris on the query processor team. My role there is architect. I spend a lot of my time talking to customers and learning about what sorts of features work and don't work in the engine so that we can figure out the next round of features to build to help you in future versions of SQL Server. I've spent 13 plus years at Microsoft. I did a little stint outside the company playing with startups and consulting. Right now, we're working on next generation features that we can't tell you about, but we have been spending the last month or so trying to figure out how do we put together a presentation about what are our best practices about debugging the problems that come to us. And a lot of the wisdom in this talk is really the horrible problems that our bosses send to us to go debug because they don't have anyone else to debug them. And recently I wrote a book about the optimizer. That's probably a more hands-on version of David DeWitt's talk today. It's in the SQL Server 2008 internals book. And I also write a blog that some of you have probably heard about, Connor versus SQL, where I answer questions from pretty much anyone about whatever questions you have about how the internals of the query processor work. Our goal is to demystify some of the hard parts of the system because it is hard, but it's also not something that's beyond anyone. If you spend a little bit of time looking at it, you can learn the same tricks and techniques that we use to debug problems. So for this talk, Boris will be doing the first half, and I'll be doing the second half, and we'll be both answering questions throughout the talk. Okay?
So I hope you can hear me still. I put the mic on the sort of on myself so that I don't have to hold it when I'm doing the demo. So how are we going to cover these topics today? First of all, I'm going to tell you about some basic information, basic ground rules which we use for troubleshooting. They're sort of obvious, but they will help set the common ground for future discussions and examples we're going to consider. Then we'll look into some methodologies and tools available we use for performance troubleshooting. And then I'm going to go into demo of the specific problem, the parameter-sensitive problem, where I'm going to show you a few examples. This is just one example of many other varieties when the query optimizer may have a bad plan choice, and I'll explain what the bad plan choice means. And then we'll go into examples as I promised before. So what are the ground rules of the troubleshooting? First of all, you need to know where to start looking. You need to define the problem, and you need to know, ideally, you know what has changed. So you have collected the baseline, and I know in many cases we are seeing people have not looked at this, people have not looked at the system before they actually run into the problem. Usually that translates to the fact that I don't know what to compare to, but there are tools that help me understand what the choices are. Again, understanding what the system does behind the scenes help me find the places and tools where I'm going to look into. And again, I'm going to show that on examples. The second important part of the troubleshooting is you know when to stop. So you're not troubleshooting because you can and because there are tools available, but because you want to fix any particular problem. And ideally in such cases, you want some objective metric you're trying to achieve. So you're not just changing somebody's perception, but you're changing, let's say, CPU bound time, CPU utilization of the server decreases from 80% back to 50% as you have seen before. And usually when you're doing the troubleshooting, you're getting rid of one bottleneck and you're immediately running into another. So there's a point of diminishing returns principle which helps you sort of stop at the right point. Don't spend more time after you reach your desired goals. One of the things we often see when people debug problems, people sometimes run into the system limits as opposed to having a particular resource bottleneck and particular inefficient use of the resource. And in this case, you need to be aware of what your system is capable of in the first place. Now, understanding how the system works helps you understand what interdependencies you're going to see. And usually, if you're looking at the problem, most likely the causes of that problem somewhere far before the symptoms you're actually observing in case of debugging the system. And obviously knowing the tools and sources of information helps you understand that problem faster and better. So what are the typical scenarios that come to us? You get a typical system slow call and you start looking for two classes of causes. First one of them is your system gets overall slow and you can't really tell what exactly with the system is happening. And in this case, we are past the stage when we actually don't know anything about the system. We actually know we can't identify any particular query or there's a small subset that has changed from what I have seen before. So in this case, you normally look at some global picture or environmental causes, and you look at the global system behavior. So a few examples I have on the slides. For example, you have memory pressure. You started some other instance of SQL Server or something else that keeps pushing the instance you're actually concerned about. And it doesn't let it run at its prior capacity, prior ability in terms of memory usage. Or your I/O subsystem got overloaded by something else that is not necessarily SQL Server related. And then there are some global system behavior. For example, you have changed something in the system that causes purging of the plan cache, and suddenly you're seeing recompile of all the queries you have been running on the system, and given the systems are now getting bigger and bigger, have more and more memory, that actually gets a heavy toll on the system itself. The second set that is more closer to us, and that's actually coming more frequently to our team, is you have a single query or small identifiable subset, which you actually consider important to you or to your workload, became slow. And in this case, you focus on the efficiency of the query plans. You're looking at the statistics and cardinality estimates if there are any problems in those areas. And then you're also trying to understand if you're looking at the so-called out-of-model cases. So what David was saying, David DeWitt in the morning about the query optimizer. Query optimizer tries to reason about how your query could be executed the most efficiently, and it makes educated guesses. Sometimes it has the information, sometimes it doesn't. So one example when query optimizer doesn't have it, let's say you have a table variable. Table variable today in the implementation that exists in SQL Server today does not have a statistics on it. So optimizer, when it first time compiles the query, actually doesn't know how many rows you have in the table variable. So when it tries to come up with a good plan for that case, it considers there is only one row. And I'm going to show you in an example on how you can sort of work around that example, work around of that problem to actually get a better plan choice in the optimizer. So in this general part of this talk, I'm going to focus on two general classes of problems. One is the excessive compilation and recompilation. So again, the reason you want to, you don't like the compilation and recompilation is because it's CPU intensive. And you want as much reuse of the plan as possible so that you can avoid extra CPU time incurred by the compilation. And you also would like to avoid unnecessary recompilations that cause that result in the same plan. So you're actually doing the extra work to come up with the plan, and all you're seeing the same plan being produced over and over again. So what you need to look into is why you recompile in the first place. Is it something that you really want the system to do, spend resources on, as opposed to actually using and reusing the plan?
How many people have had recompile spikes? Yeah, okay, good.
So basically that's a common problem, and Then the another one that comes with the recompilation, you might have environmental changes such as statistics or something else, parameters that may cause us to cache the bad plan. And bad plan in this case is the plan that is inefficient for the other set of parameters for the other most frequent queries that you are submitting that are going to use the same plan. Now, the reason we cache plans, we want to avoid the time spent on optimization because it's a complex process. Now, sometimes you can afford recompiling query over and over again, and usually it's a trade-off between how much time is spent on the compilation and how much time is spent actually on execution of the query. Obviously, for the OLTP-like systems, you won't compile once and then reuse the plan because queries take milliseconds or less. For the data warehouse systems, you actually can afford recompiling query for every execution or for every invocation of it, because the query may execute for minutes or hours, and few seconds or even minutes taken during compilation is actually insignificant to the benefit you're getting for a recompiled query at this point in time. So how can you detect compilation and recompilation? You can look at the SQL trace event, SQL statistics batch requests, and SQL compilations per second. And if you see the high ratio of recompiles to the ratio of incoming requests, you obviously can investigate why are you seeing this, and if this is desired behavior of your system, if you can change it in any way. If you want to look in the DMVs, and I'm listing a couple of them in here with a few specific columns on them. So one of them is DMExec query optimizer info. And if you look at if the snapshot this DMV and you look at the optimizations count and elapsed time counters increasing constantly, that means you're constantly going through the optimization. Again, depending on how fixed your workload on the system, it may or may not be desired. You need to look into what gets recompiled. CSDMExec query stats has a column named plan generation number and execution count. You can compare if a particular query gets always a new plan, so this plan generation number is going to be increasing. In 2008, we introduced two new columns in CSDMExec query stats. One's called query hash, another one is query plan hash. Those two columns help you understand if the particular class of queries stripping off the literals are getting compiled into the same plan. So basically, even if you have ad hoc queries with the different literals, so they're not precisely matching as the text, are going to be generating the same plan. So you can look for the opportunities to either parameterize those queries and minimize the fact that you actually have to compile them over and over again. Now, what you can do in case of excessive compilation and recompilation. So you can monitor different set option changes. As I mentioned, they cause the plans to be incompatible in the plan cache. So when we compile the first time, we gather a lot of information about the state of the system and state of the session, and then put it in the cache. If you change any of this, the plan becomes incompatible with the invocation going forward. Then if you're using temp table versus table variables, as I mentioned, table variables do not have statistics on them. It might be good or bad, and we'll look at an example. Then you can use either keep plan or keep fixed plans to avoid changes due to statistics. Again, this might or might not be desirable depending on what kind of changes you're seeing. And then you can, at the same time, you can either turn on or off automatic statistics update. It's on by default. Again, we're trying to keep stats up to date, but in some cases, it causes the system to spend time actually updating stats and generating the inefficient plan relative to what the workload looks like going forward.
So for the people who were at the Let's Talk this morning, there was a question at the end about queues, using queues as table. How many people heard the queue question? Yeah. So some people will insert rows into a table and then immediately remove them. And so they're constantly inserting and removing tables. This tends to be one of the areas where our automatic statistics algorithm tends to fall apart, because the assumptions of that algorithm are that you're going to keep adding data into a real table instead of just constantly emptying it all the time. So understanding what the relative limits are of what that automatic algorithm can do for you can help you figure out when you might have an out-of-date statistics problem. So typically, a table that's normal size, not a big data warehouse table, and not a queue, will have relatively good behavior out of the automatic statistics algorithms that we have now. However, if you get into cases where you have really, really small tables or really big tables, it could fail for different reasons. In the case of the small table, you're always behind. When you create the stats, they're immediately out of date. In the case of the big table, the thresholds for when we update the stats is so high, it's 10% of the table, that often you never hit it because the table's so big that 10% is just a huge number to try to meet in terms of rows changing. So understanding those limits will help you know where to guess when you try to look at your plan problem and figure out where it is. Yes?
Yeah, so we're an ISV, we run against different databases. So in Oracle, our solution for that is to drop the statistics. And then it uses heuristics. And DB2 has declarative syntax where you can declare a table as being volatile. Have you thought about stuff like that?
So the question was, other vendors have different ways of dealing with statistics. Have you thought about changing the way you do statistics? Is that right? Paraphrasing. For this problem, yes. So I will say that the fact that we've gone and looked at it and we actually even internally have names for most of these problems is such that it's not a question of us not understanding what it is we're trying to do. It's a question of, from an engineering perspective, how do we safely deploy new changes to our customer base so we don't cause plan regressions whenever you get the new version of the product. Because even if we were to go and fix that, it can cause other issues elsewhere where an existing good plan can turn into a bad plan if we're not careful. And this talk isn't about how the optimizer works in that regard, but it is one of the reasons why we have to be fairly careful about how we evolve that product. So yes, it's my job to try to figure out how to make that happen. And as I tell people in all of my talks, it's my problem. It's my fault your query is slow. And blame me for this one. Yes, my problem. I'll work on it.
Okay, so we'll take another question and then we'll move on. Go ahead.
So a lot of the examples around compilation and recompilation are about what happens to stored procedures and queries within stored procedures. Does all this apply to queries that run directly against a database, just as individual queries outside of any kind of object or procedure or function?
Yes, so the general sense of this, yes, you can apply those.
Repeat the question.
So the question was, does this all apply to the queries executed inside of the stored procedure? So does that apply to the ad hoc queries or queries directly executed against database itself? The answer is yes, you can apply those principles against any kind of query going against the table itself. The difference between the two, in a stored procedure, you usually have much higher controlled environment of how the query is changing itself. So you have high repeatability, and you can actually have higher chance of reusing the plan for that query. And as many of you probably know, that if we're caching the query based on the exact text down to every single space inside of that batch submitted to the SQL Server, to the query optimizer, so that if you're changing even the space at the beginning, a comment at the beginning of the query, it's a considered different query, so you're going to incur the recompile. For the stored procedure, this is not the case because this is a fixed text you're going to execute. So in that sense, it's better. But general principles do apply. So I'm going to defer the rest of this list, which you can look up at the reference at the end of the deck. So we have the performance troubleshooting white paper, where we actually have examples of few things that happen. Basically, why, for example, mixing DDL, DML statements wrong. But the basic idea is that the optimizer does not know what's going to happen before it executes your batch or your stored procedure. So it has to guess. And when it uses the guess, it might get it wrong. And when it gets it wrong, that's when you get the perception of the inefficient plan. Basically, help the optimizer to make the right choices. And there are a few things you can sort of follow as best practices to avoid forcing the optimizer making the bad choices. And with that, let me go to inefficient query plan. So inefficient query plan is actually a misnomer, and it's a slowing down of the query for the particular query. And you're usually seeing contention of some resource, CPU or I/O, for example. Now, you can usually start looking for offenders for something that's abusing the resource using sysdm exec query stats DMV. And if you have a baseline, if you know what has changed, that's relatively easy to find.
How many people take baselines of their systems using DMV exec query stats?
Well, this is a pretty advanced crowd, so
Good.
This is probably half or more.
The rest of you should.
And this is sort of paraphrasing what David DeWitt was talking about in the morning. So query optimizer takes various inputs. It could be stats, it could be parameter values, and we'll talk about that specifically. Looks at the physical database design, looks at available indices on the system, and then it tries to reason about selectivity and cardinality. It uses those incoming inputs that you provided, the system provided, to come up with a good plan, the most efficient plan and the cheapest plan, given the information it has at that point in time, at the time of the compile. And remember that you compile first and then you start executing. So actually there's a difference between the two events might introduce some changes that cause the plan to run slower. Now, if any of that information gets wrong, you're most likely going to get what's considered inefficient plan or the bad plan. So to give you a visual example of this, let's consider this simple query. You have a simple select and you have a predicate on column A, which between two constants. So that's relatively easy. You have one index and you have covering columns B and C. This is optimal in this case. Now, if you add a little bit more predicates, you will realize, well, I can have actually two indices, A or B, and then covering columns B, C, or AC correspondingly. But I can see which one is more selective and pick one, the most efficient, that gives me the fewer row at the very beginning of the query. But then if I introduce more, sort of complicate the query a little bit more, I have more columns. It's the same table, more column, but now I have even the function, some computed value in the predicate. That becomes it. I need to introduce yet another index. But let's say there's not enough storage for all of those indices. So which one should I pick? There's quite a variety. Now I have to pick one, and if the optimizer actually has a choice for that, it has to cost this, and as you have seen today, the cost accumulates and the error propagates going up. So I can actually have some random choice in this case. Now, and I'm not talking about updates or anything else that might be even more complicated. So what we're seeing here is it's sort of easy in the very simple queries. Then we have to guess and use statistical information. And then we're giving up because we haven't looked at the parameters, we haven't looked at the views, we haven't looked at the more complicated data types. For example, the character data types where collation also matters. And we looked at the very, very simple query versus the actual queries look more like that. And it's actually one of the queries that Connor worked on, and he has an example of working with this particular application later on and the kind of debugging he has to do. Now, so what are the sources of inefficiencies? What optimizer can get wrong, and why this whole system of guessing the correct plan or coming up with the correct plan breaks? So first of all, you can have bad cardinality estimation. The tool to use here is the statistics profile. So it's a very, very powerful tool, and usually if you use SSMS, you can look at the actual plan. So it will tell you if the estimates that were optimizer assuming about this query actually matching the actual number of rows that going through the query. And just very, very large discrepancies in here are going to tell you that, hey, maybe that's where the optimizer guessed it wrong, and so I need to somehow tell the optimizer if he can come up with a better plan. Now, it could be because the statistics are stale, so the optimizer actually didn't have access to the correct information, or it could be design limitations, what we internally call out-of-model cases. So, for example, you have a function that takes, I don't know, second digit out of the 8-digit year, and we can't really guess what that function is going to return given your probability distribution of all the dates you have in database. Even though we have most correct statistics on the dates themselves, we're really having a hard time to come up with the third digit of that number is going to be. There's no easy way to estimate it during the compilation. So in this case, we're guessing, and this would classify as out-of-model case. And you should be aware of such cases when you're seeing them in the plans. And finally, you can be seeing that there's different parameters which we're going to use as the means of picking one index over another and estimating the selectivity. They're not the most frequent parameter that is present on the system. So it actually might come up with a plan that is efficient for this particular set of parameters, but it's not good enough for the rest of the workload being submitted on the server. This is parameter-sensitive plan problem. Or you might simply have bad physical database design, so you might have not enough indices or incorrect indices that do not include all the information optimizer needs. So it has to go to the base table to look up all the columns you're asking for, incurring additional random IOs against the table. Now let's look at a few examples. So the table variable case that I mentioned before. So you usually see the bad query performance when you use table variables or similar concepts such as table value parameters or table value functions. And you join those table variables in some queries, and they have relatively large data sets in the variable itself. Before, it wasn't as common. Now it's becoming more and more common as the system gets bigger and bigger. You have more and more memory. So actually, people pack, I don't know, 10,000, 100,000, a million of rows in the table variables and expect the correct queries. So what the optimizer does, it doesn't really know when it was built. It didn't really care how much rows in that table variable. So it actually assumes 1. And when it assumes 1, it uses that choice to evaluate the rest of the plan. So it comes up with a plan that has a relatively small number of rows assumption in table variable. So how you can detect that? You can look at the statistics profile and see what the system actually gives you and what the actual number of rows coming back. So here's the screenshot example of what the statistics profile looks like in SSMS. So this is the query that has around 10,000 rows in table variables. And then there's a real table with about the same number of rows. So I'm using the simple join on the column on that. And what I'm seeing here is that in this particular case, the number of rows that coming out of index seek is actually 10,000 versus the estimate number of rows is only 1. Actually, in this case, we also have 10,000 executes. But because we have nested loops for every row that coming out of the top table, we're using the seek into the second one. So because we assumed only one row would come up out of it, this was actually very, very efficient plan. And instead, we actually did this 10,000 times. So we incurred 10,000 IOs. And in this case, that was an efficient plan. I'll answer your question in just one second. So one way of avoiding this, now we have a statement level recompile. I think it's big enough, no? All right, better. So I was assuming you have seen the statistics profile, but good point. So I'm going to zoom in again. So what you're seeing here is the estimates on the table scan above is only 1 versus actual we get 10,000. So in this case, that's what actually causing the plan to behave badly. So we're doing the index seek, which we assumed we're going to do only once, but instead we're doing 10,000 times. So the way to fix this problem with the table variable specifically, when you introduce the option recompile on that statement, so even though you have compiled this batch or you have compiled this query, the time we reach this point in the execution, we're going to recompile this again. But because we are in the process of execution, we actually know exactly how many rows in the table variable itself. And what you can see from this particular point that in that second case, sorry, I'm going away always. So in that particular case, I actually get the correct estimates of the row. And instead of doing the seek, I'm doing the table scan. So instead of doing 10,000 seeks and 10,000 random IOs in the table itself, I'm only doing one table scan. And I'm using hash match instead of nested loops. So that's what makes the query efficient. That's how the optimizer actually made their own choice, because it didn't know what your table variable may contain. So that's one of the options to fix this particular problem with the table variables. Now, with this, let me go into demo, and let me set the problem of what the demo looks like. So in the demo, I have the very, very simple query encapsulated inside a stored procedure. And it uses one join column between the table and two seek columns each on the corresponding table A and B. And what I have in this case, if I have submitted the parameters, so I constructed the data in the tables in such a way that if the parameter value is actually low, so I have the values in the range of between 0 and 10. So if the parameter is low, I have very, very few rows. So the predicates are usually very selective. And I have a large number of incoming parameter 1 or 2. The number of rows in a table is relatively large. So the optimizer has a very, very high chance of making a mistake if I'm giving him in the corresponding low selectivity or high selectivity range. Now, what happens in this case, one set of parameters is relatively frequent, another one is relatively infrequent. So if I'm giving the parameter that is frequent, I get a plan that works well for both set of parameters, for frequent and infrequent, and it's efficient in both cases. For the second case, it's actually not going to work for the frequent parameter. So let's say if I picked infrequent parameter, similar to what you have just seen in the table variables, I'm trying to do the nested loops, and nested loops actually gets a severe underestimation of how many rows are going to pass through the query, and it produces a lot of random IOs on the system, which causes the query to run slower. So displaying this graphically, so if I have a parameter which is in the common part of the table, I'm going to get the plan 1, and that plan 1 works relatively well for that particular value itself, as well as for the rest of the parameters. That's a fast enough part. Now, if I get an infrequent parameter first, I'm going to compile this query using this value that I looked at in the incoming parameter store procedure, and I'm going to get the plan which is fast for this particular set of parameters. But because it severely underestimates a number of rows on the frequent parameters, I'm going to get the slow plan for the rest. This is what you normally perceive as the slow down or the perf regression on the system. So that's the second upper right corner of that table. So let me go into the Management Studio and demo that. So what I have here, and I'm hoping you can see that, that's the query we were just looking at on the slide, join into two seek predicates. So all I'm going to do, I'm going to define that table, define that store procedure and run it. Now, and I have two workloads. So what I'm doing here with the workloads, I have 100 invocations of that store procedure, which you're seeing here. And they just give random parameters to the system itself. Now, what I'm doing before I'm starting this invocation, I'm going to clear the procedure cache from the previously compiled file, and I'm going to use a particular plan handle, which I'm going to look up by the name of the procedure. Again, this is a feature of 2008 where you can purge any individual entry out of the plan cache as opposed to purging the whole plan cache itself.
So this would simulate a workload over a day where you start up the server maybe at the beginning of the day, and whatever the first value is gets sniffed, and that's the plan that gets cached.
That's correct. So the first parameter we use, that's the one we're going to compile for and use, and then we run the rest of the workload. So as you can see here, the workload executes in less than 1 second, which is good day, everything works as desired, nothing else happens.
Of course.
So you have a question?
Yeah, so
go ahead.
It's always an assumption that there's only one record in that. I've got a fairly stable workload. We use table parameters. Is there a way that I can change the costing? Is there where I could change the costing from 1 to 10,000 instead? So it always assumes there's 10,000 in the table variables?
So there's a question about table variables, the prior example.
Yeah.
Okay.
Okay. So can we change the costing for table variables? No, you can't change the costing for table variables.
Can I ask you to change it?
You can ask me to change it, yeah, and then we'll go look at it, sure. But it's a bigger problem than just fixing the costing, right?
Well, because I know I can change costing. There's
No, you
undocumented stuff.
no, you can't.
No, you cannot change the costing. So what you can change what optimizer thinks about that particular case. But in case of table variable, the only thing you can do is the option recompile thing. You can do the hints, which I'm going to show right in this demo. So for your bad day, you saw the prior workload, 100 invocations of that store procedure completed in about 1 second. So for the second query, what I'm doing here, I'm clearing up the plan cache out of this particular query. Again, this is the same part of the code. And instead of submitting the common parameters that give me the most frequent value in the table, I'm going to give it the values that are actually representing relatively small subset of the rows in the table. So that's a different set of parameters, and I'm going to execute it again. Now, what you're seeing here is that actually the query continues to execute, and the prior one was executing in just 1 second. This one keeps running, and actually it's going to run for about 5 minutes. Now, and this is the case where you usually get the call at night, and the system is slow, the web page times out, so what happened?
How many people have gotten that phone call? Yes.
Excellent.
Welcome to the club. I have a little support group.
So obviously you have collected the workload, you have baseline, so you immediately can tell this is the query that changed the plan, and all you have to do is just do the recompile of that particular query, and everything good. Now, unfortunately, we haven't collected anything. So all I'm going to do, I'm going to look at our typical DMV, DMExec query stats, and cross-apply it with the DMExec SQL text. And all I'm going to do is just find the largest consumers on the system in this particular case. And what I'm seeing as the result that I have one query that uses a lot of time on my system out of top 5, and I immediately recognize that's my create procedure, which you see the fragment of on the right. So if I'm going to scroll to the right, you will see that exactly that's my store procedure. And there's some query that runs inside of that that's consuming all the CPU on the system. So that is my problem. So what I want to do right now, I have identified any single query that is going to actually affect my workload, and I'm going to look at its plan. So what I also have collected in this particular query, or gathered from DMExec query stats, I have a plan handle, and all I'm going to do, I'm going to manually copy that plan handle into DMExec text query plan. And by doing so, this will help me to look at the cached execution plan. And I'm also using the statement start and statements end offsets to pull the query for this particular statement inside of the store procedure. So if you have multiple statements, you actually can pull it for individual statement itself. So once I run it, I'm going to get the XML show plan, which I'm receiving right here. And by clicking on it, SSMS displayed it as a graphical show plan. So what I'm seeing here, and you're already probably anticipating what happened here, I'm seeing the nested loops here. Now the key point in here, this is the plan I have compiled, and that's the plan that I actually put in the cache. So I don't know really if the system actually getting different number of rows through this plan, and that's why this query is slow. All I know is that this is a particular plan I'm looking at, and that might be inefficient relative to the query I'm observing. So let's say if you have actually did collect the baseline itself. So what I'm going to do, I'm going to run the good workload again, and it's going to execute in 1 second, couple of seconds again. And if I get back to my exploration example and look at the top consumers again, so again, I'm going to get the same set of queries. I'm going to pull the same, actually now different plan handle, and plug it into DMExec query plan DMV. And once I execute that, I'm going to get the different plan, the plan that I have seen for the good execution of the query. Now, if I compare the two, I immediately will see that there's a nested loop and hash match flip between the two. And that's the good indication that, yes, I have flip-flopping of the plans between nested loop and hash match. And this is just one particular example of how this problem may exhibit itself. So there might be other ways you can observe this problem. And they could be different choice of the clustered indices. They could be different different plan shapes, join order, and other things that you can actually watch for. But in this particular case, what helped me, I know what the good invocation of the store procedure was and what the bad was, so I can actually do this. If I have collected the baseline, if I have snapshotted this before the problem happened, this makes it actually very, very easy when the problem actually happens. And again, what usually helps us, and we have seen this enough times, so that's one of the few things we verify first, that something like this happens. And I know the stored procedure, nothing really changed in the system, so the only thing that is changing is the parameters. And usually people say, hey, I run dbcc free pro cache, and the stuff suddenly starts working. So that's immediate indication that you might be having the parameter sensitivity problem. So in this particular case, how I'm going to fix it? The way I set up the example, I know that I'm going to, I have one plan that actually works well for all. So in the 2008, we introduced this new query hint that's called optimize for unknown. And what it does, instead of looking into a particular parameter passed to the stored procedure, it uses the parameter most frequent that is available from the histogram defined on the table, computed on the table. So it actually will pick the most frequent parameter and optimize if that is parameter passed to the stored procedure, not the parameter you actually do the first invocation of stored procedure. So that helps me to get the most likely, the most efficient plan for the most frequent parameter. Now, if I run this, and if I going to go to my good life and bad life examples, so let me bring them back. So if I run the good plan, it completes in about 1 second still. And if I look at my bad plan, which was used to take about 5 minutes on this laptop, it still completes in 1 second. So actually, I have fixed the problem. Now let's take a look at what happened actually with inside of the system. So let's look at our query that investigates what the consumption of the resources on the machine was. So I'm going to run this query again, and I'm going to pull the plan handle out of the query, which again happens to be my store procedure. And now instead I'm going to copy it to same dm exec query plan text. And what you see here, and actually compare it with the good plan we have before, then now I have the plan that corresponds to the hash matching. So I actually, by introducing the hint optimize for the unknown, I have produced the plan without really any dependency on the past parameters in the first place itself. So this is one way of fixing parameter-sensitive problems. And this is the case when you can actually have one plan for all that fits well. There are cases when it wouldn't fit. So there are cases when you have to introduce the logic of if then else and actually look at what the incoming parameter is, when actually there are two plans that are good for one set of parameters and they're completely incompatible. So there's a question.
So why did you change that to use an optimizer hint instead of just putting the hint off and saying use a hash match?
So read the question.
So the question was, why can I just use the hash match hint in this particular case? There are multiple ways I can affect the choice. And in this particular case, I knew that the parameter sniffing problem, the fact that we actually look at the parameter value and use it, that's what was causing me the problem in the first place. So it's a trade-off. So when I give a hint, I always restrict the optimizer to not consider certain choices. If I give the optimizer the particular directive of saying don't use any other join strategies, I'm actually in the complex queries, I might be producing some other bad plans, or I might not be getting the desired result. So I want to hint as little as possible. At the same time, as soon as it produces the results, that is sufficient for me.
So hints might not work in a complex query. And also, if your system evolves and another plan choice becomes optimal as you add more data to your system, you're going to be potentially blocking that by using a too aggressive hint. Doing just the little tiny hint that you need will guarantee that the system achieves the stability that you want for this parameter sensitivity problem without restricting the search space elsewhere. Now, you can manage all your plans carefully all day, every day, or you can just take the little tiny hammer and hit it in the spot where it needs to be hit. This is the take the small hammer and hit it in the spot where it needs to be hit. There are large sledgehammer approaches.
So I'll answer those two questions in just 1 second. So one other thing you can look at, so when you look at this show plan XML that you pulled from the cached query plan, and if you look at the properties, so one difference you can observe, if you pick the top level select in here, you can see that in the properties windows, you can see the parameter list. So parameter list actually tells you what values were used when this query was compiled. And remember, the one on top is the one, actually, I'm going to zoom in on this so that on the back you can see it. So you see the parameter list, that is properties of the very, very top select of the plan, and you see 5 and 5. Those are the value that were used to produce this query. Now, remember that we fixed the procedure by removing ability to sniff by saying optimize for the unknown. Now, if I select this plan that is being produced out of the optimize of the unknown, you see that there's nothing like that in the properties of this window itself. So we have not used the parameter values to get this itself. So you can also find this in XML show plan itself. So that's pretty much the example we wanted to do. So let me answer those questions. Go ahead.
Actually, you already answered the question. So optimize for unknown disable the parameter sniffing.
So the question was, does the optimize of the unknown disables the parameter sniffing? It doesn't really disable the parameter sniffing. It makes this query use the value that is derived from the histogram, the average value, to reason about the plan, reason about cardinalities of things that are participating in production of the plan.
It still sniffs a value. It's just an average value.
So back to the deck. So a couple more. So one more question. Go ahead.
The trace flag that was introduced in cumulative update 7 that to deal with the, I'm just asking, does it do it? Is it
My Lord, you guys are all about every single little tiny knowledge base. You shouldn't be using that thing unless you have a monster problem. How many people here have used that trace flag?
Which trace flag?
Okay, it's just you then.
You just say that.
So there's a trace flag where we introduced some magic special code for one customer whose CIO complained bitterly, and it doesn't work for everyone. But basically what it tries to do is learn about ascending keys.
learn about what?
Ascending keys, which basically is how frequently you recompile stats.
Okay, so it doesn't optimize for unknown as a
There's also a trace flag for just saying I always want at an instance level to optimize for unknown. There's another trace flag for that. And you shouldn't use that either, unless you're a CIO who's about to take all your money and run somewhere else. Right? Those trace flags are CIO trace flags, not DBA trace flags. When I go to Technology Week or whatever, then we'll talk about using those trace flags.
So when the developers tell me that they don't want to go and refactor all the
No, you tell the developers that they should be making sure their code is up to date and clean. Because if you go and just have a bunch of code and you don't know what it does, then what does that say about your app? Right? You can't debug it. So no, I mean, then you're going to call CSS and they're going to have to figure out, oh, you've got the magic trace flag on. Now, the magic trace flag is just to deal with massive old legacy systems. New development, you should never, ever use it.
So go ahead.
We tried. We have a query with a date range, and the parameters vary, but the date ranges are like 5 different ranges, regardless of what the parameters are. So I tried putting in a comment with the size of the date range, and that seemed to create different query plans. And I'm worried that will get optimized, the comment will get optimized, normalized out, so they'll end up just looking at the same query string. Is that safe?
So the question was, so the gentleman has a query where he puts the comments related to the date range inside of the query itself, and every time you do that, you get a different query plan.
There's only like 5 different possible ranges.
5, anyway, so...
We only get one plan, so...
As I mentioned before,
is too many.
for the purposes of the recompile, we use the exact query text down to every single comment, and that is considered a different plan. So even if you annotate above that this is the time I have submitted the query, but as the part of the batch, it doesn't matter. So if it's even if you just introduce an extra space between from and from, again, I can show you this probably in right here. So if I look at my exploration query, right? So you remember that. Just one second. So I guess I probably will. I'll do that offline. So what I was going to show, if I skip just a part of the comment, I'm gonna compile a different brand new plan. So that's the deal in here. So let me quickly finish that part and then give it to Connor. So there are a few things you need to be aware of. So a lot of troubleshooting information that you get from a dmexec query studs, it's bound to the plan cache lifetime. So if there's any operation you're doing that destroys the plan cache entries, you're going to lose that information. That's why snapshotting in this particular case is important. So there are a few SP configure options and a few database option changes that will destroy the information. So you should look for SQL error log events that indicate that the plan cache was flushed, so which means you lost your debugging information. So this is the list you can consult later on. I'm not necessarily sure we document every single one of them that it flushes the plan cache. So if you globally change any of those options on the server, you will destroy the plan cache contents, which means you destroy your troubleshooting information. Similarly, you can do this for the database options. So if you change any of those options on the database itself, you will destroy entries dedicated to that database. Again, be aware of that when you're doing the troubleshooting. And here's the example of the particular troubleshooting case.
Can you guys hear me in the back? Make sure I get this right. Yes? Good? Okay, wonderful. So what I'm going to do is to tell you about a few real-world examples that I've had to go through where my boss comes to my office with some horrible problem and there's no one else to debug it. And the intent here is not to show you how to debug a really hard problem. It's to show you how the same techniques that we've described here in the first half of the talk apply for the smallest of queries and the largest of queries. And eventually we got to the point in most of these where we were able to make progress on all the public APIs and public tools that are available using stats profile, looking at the show plan XML, understanding what the estimated versus actual for each of the plans were. And that made a lot of progress on most of these queries. There were some cases where we actually also did additional work inside of the engine. That's not really important for here because most of the lessons are you can make great progress even on the nastiest of queries just by understanding a few simple tricks. Look at where the stats profile is and see how far the estimates versus the actual are and understand what the query operators do, and you can make a ton of progress. Anyone can do it. People think that I'm somehow good at it because I do it on these big queries, but I'm not doing anything different. One example that we worked on was an internal database that we have at Microsoft, and it keeps track of every sale of every piece of software that we have through every channel. So instead of just having one fact table in a data warehouse, we have 10 or 15. And for each channel, there would be the budget, the actual, and the plan. Those are each a fact table, and there's dimensions on those. And so you'd have a channel for retail and a channel for ISVs and things like that. So it's a very, very big data warehouse, and every time there's a sale, you could capture this week's sales through Best Buy in Illinois or somewhere, some city in Illinois, right? And so it's big, and they have these huge queries they run on it. We use this to do financial reporting and estimates about whether we're going to make our budget numbers and sell as much software as we think we're going to sell. And so whenever it doesn't work, you can imagine that the executives get very antsy. So one day, the executives got antsy because we had installed a new internal build of the server because we run all of our own software on pre-release versions of SQL Server before we ship it to you to prove that it works. And, well, let's just say it didn't work yet. So this was on 2005, but it doesn't really matter for this particular case. So we have lots of queries that various analysts are doing to figure out what's the sales that are happening here and trying to figure out how office sales are doing in this city versus that city, et cetera. And they have these big queries they run. In fact, the queries are so big that they can't run it on a single box. They took 5 or 6 of the largest boxes they could buy, and they put them all up in a big array, and then they would just round robin and send each person's query to the next one. So 32-way boxes, each of them running queries, and they were all taking so much memory that the whole thing was just grinding to a halt. All these machines were just falling over and returning out of memory for every query. Then they call me. So the basic pattern on these is just like the fact table example you saw in David DeWitt's keynote this morning. The only difference being that the simplified form of it's over here. You have a group by query on top of 10 or 15 joins with 1 or more fact tables, and you have a bunch of different conditions down below. The where conditions aren't where column equals 5. It was where in list equals huge 1,000 lists long element list for each of those tables. And so it was a very, very big query, and it's all ad hoc generated by a tool. So every person goes and runs their tool saying, well, I want to look at my region. So they would go click the things in the UI. It would generate this query and then run this thing. And instead of taking 1 or 2 or 5 minutes to run, it would take 30 minutes or a day to run, assuming it finished and didn't run out of memory. So they would often like to iterate on these. So if you have slow queries and it's substantially slower than your prior release, the first lesson is you can't ship a new version of SQL Server. The second version is what do you do? How many people have heard of DBCC memory status? Yeah? So this is a tool to let you figure out how each of the components inside of the server are actually using memory. And in this particular case, the optimizer was using all the memory. Now, I don't know about you, but last I checked, just doing a little mathematical model didn't return any query results to anyone. Right? Figuring out which plan it is and taking all the memory in the server to do that doesn't answer your question. We have to execute the queries in order to do that. And we weren't executing the queries. We were using all the memory in the system just to compile them. Each particular query was taking over 200 megabytes. And if you have a 32-way box, you figure you could handle at least 32 concurrent large connections at a time. But since they're 200 megabytes and the average 32-bit server can handle about 1.5, 1.6 gigabytes, you're only really compiling a couple of queries at a time before the system falls over. So in the proverbial sense, there's your problem. So how do you fix that? Well, how many people have heard of the memory gates that we added in 2005? Right? Well, this is one of the reasons we added this. Ultimately, memory in a default system could be allocated just to whoever asked for it next. But in most of the things that you have to do in high throughput systems, you actually need to reserve memory. And the reason is because otherwise you're going to run out, just like this. So here, what you actually want to do is, if someone's going along and optimizing, and we're searching through all those millions and millions of plans, trying to find a good one that can execute in reasonable time, well, it'd be really nice if that thing could finish, instead of getting 99% of the way through and then running out of memory. I'd rather kill something that just started rather than one that's been optimizing for a while. So the takeaway is, we actually wanted to bias the system to give memory to compiles that had been running for a long time, under the assumption that they would finish sooner than ones that were just starting. So we have this big dynamic system we created and patented and all sorts of stuff that basically what it does is tries to figure out how to be fair. So instead of having the system have to return out of memory after you've done 99% of the compile, we will actually finish that and we'll slow down the compiles of other queries. So the overall number of queries making progress in the system at any time is slower, but amazingly, this system ran 30% faster and didn't have any out-of-memory errors anymore. The takeaway is that even if you don't have access to the source code, this same problem can exist in any large-scale app. How many people have run into cases they just overload their system with requests? Right, the answer is you need to throttle them at some level, right? You need to figure out how do you throttle your client connections. Either you can go through, in this case what they also did on top of what we did was to add a service broker queue for all queries. You would submit it into a queue and then the queries would be pulled off the queue and executed in the system. You can do that in your own client tool as well to make sure that if the system's overloaded, you don't allow the users to continually just stomp the system with requests. These large-scale request systems are difficult because you often have bought the hardware long before you know what the limits are in terms of what you can execute. And so having to adjust to that is something that a DBA often is faced with without knowing anything about the application or anything about the number of users they have to satisfy. Getting that right is very tricky, and is something that often a consultant can help you with if you can't do it yourself. Speaking of, Erlen.
Okay, so another thing, did you fix the long in list? Because I know that is one thing that is
Right, so the question was, what do we do about the in list, right? So for those paying attention, there were all these in lists down there. We actually added another optimization that helped turn the in lists into something that used less memory as well. Yeah, so just so you know, if you have a really big in list in a query, it takes you 2 or 4 bytes to write each element in that in list. By the time it gets translated into the internal query plan, each element in that in list takes about 1K. To do all of the magic properties and statistics and stuff that we do, it's about 1K. So it's potentially much, much larger than the size of your query text. So after you get to about, was it 64 or 100, some number like this, we actually automatically turn it into a special constant internal temp table thing for you. And that way it bounds the amount of memory that it's going to take, so it's not going to destroy you.
You didn't fix that?
Yes, well, maybe we didn't fix it to your satisfaction, but I can assure you that MS Sales is happy. So I'll be happy to follow up with you, and we can figure it out if there's a case that we didn't handle. But we did do some work in that particular time frame to improve this situation in general for these large data warehouse customers.
Yeah, but what we're saying is that the application should be generated as inlet.
Should the application generate these? Well, you know, that's, again, once you get into the discussions with CIOs, that doesn't necessarily always end well for me. So if you run into this situation, you want to see, am I actually being throttled because the system is overloaded? You can actually go look at DBCC memory status and see the memory gates. So we allow a certain number of executions to compile who don't use a lot of memory. We allow a fewer number who use more memory. And in the worst case, we allow one who uses all the memory in the system. And you can see this. There's the small gateway, the medium gateway, and the big gateway because I'm very creative with names. So this can happen in any live system 2005 onwards, not in 2000, which you shouldn't be using anymore anyway. Okay, so let's look at the next problem that we had. Even after we fixed all these, MS Sales was still unhappy and they still complained. But overall, the reason why was because we had bad cardinality estimates. Imagine that. So remember you saw the number of different plan alternatives you saw for 8 joins, right? They have 15 plus. So you can imagine how bad it was for us to try to come up with a good plan in that case. And what happened is we would have this huge list of joins, and at the top of that there'd be a group by. And we thought that the joins were highly selective, but in this particular case they weren't very selective. So we thought there'd be one row coming out of all those joins, and there were 100,000. And so we would put a sort and then a stream group by at the top of that, and the sort would take lots of memory. You see a common theme here, right? We're using lots of memory all the time. But in a data warehouse, you almost never really want to do anything that spools to disk, because often it's going to be the size of your fact table, or at least in that order of magnitude, and you don't want to do that. So hash is better with fewer requests going through the system. So we can't really fix the fact that the cardinality estimate is wrong, at least not without doing major changes to the system. So in this case, we retreat was the better part of valor, and we just added an index hint, or I'm sorry, a hash group by hint. So we said every time that you're going to do a group by, since all the queries in the system are always exactly this pattern, and you never want stream group by, then just do hash group by on all the queries. And that worked. Now, most of the time, we do much better, because instead of having a very small buffer to do a sort that always spills to disk, now we have enough memory to get it to work, because we estimate the hash join to always at least take a certain amount of space, or for both hash join and hash group by. So there are cases to use hints, only when you really have to, is basically the answer. Okay, so you're going to see a theme here, which is the boss comes to Connor's office and he says, Connor, drop what you're doing. Someone's complained. Someone important's complained. In this case, it was an internal person who happens to be a bigwig at Microsoft, and they work in the developer division, and they build the version control system. How many people here have heard of TFS and DevDiv? Yeah, so, okay, version control. The internal, most average customers have like 100 users. DevDiv runs their whole system on TFS version control, and they have 3,500 users. And they have one of these cases where they're the largest installation by far, and they run into a query plan problem. And all of a sudden, when you go try to check out files, it takes hours. And again, they tell Connor, go make people happy. Okay, great. So we go look at it, and there's lots of problems, but most of them are relatively small, and we can fix them by talking with the team. But overall, there was a problem that they sent me after we got things working again that was really quite odd. They were doing an upgrade from one version of their software to the next, and they were adding partitioning. How many people have tried to do this? You have a really big table and you want to add partitioning to it. All right, so this is a common case. It's not just related to version control. Now, in their particular case, they have a 16 terabyte database, which is larger than the average database. And sure enough, they come to me with, hey, we run this query in our tests, and it runs for 8 hours and then errors. It doesn't error with out of disk space or out of memory. It errors with out of uniqueifiers. I go, okay. I'll see what I can do about that, boss. No problem. Now, it turned out this was a bug, and so what I'm going to explain to you, part of this is a bug in the code that's already been fixed, but the plan shape is really the interesting part that I want you to take away here. So we do occasionally have bugs in the server. We don't like that, but we're very proactive at trying to fix them, and we do have them. And in this case, we fixed it before the customer actually would ever hit this case, because they were doing pre-release testing of new code, and we found this case. And I can assure you that no one else has ever hit this. So I look at the query plan that runs for 8 hours, and it's this funny shape. So they're adding partitioning. And so it's a table, it's an alter index command, basically, whenever you add partitioning. So you're rebuilding an index, and the source is non-partitioned, and the target is partitioned. So if you went to my update talk yesterday, it's the one thing I didn't talk about was what does it mean to do create index plans or alter index plans. And they really are just updates at the grand scheme, at the highest level. There's additional locking and things that happen, but they're just update plans. So for those of you who had the benefit of attending my talk yesterday, you read the rows, you compute the new values, you write the rows. In this case, you read from a non-partitioned source and you write to a partitioned source. And the key there is that you have to figure out what partition you go to. Now, they had done the initial work to partition, and what they decided to do, first of all, was create a new table and put everything in the first partition, and then move everything to the next partition. So they would decide they wanted to have 100 partitions, but for whatever reason, instead of putting them all in the 100 partitions to begin with, they would put them all in one partition first and then move all the rows. Sound like a good idea? No, you guys are good. That's a bad idea. So that was the first thing I told them. Made me seem really smart. But honestly, it's just when you look at the number of rows moving around, don't do that. So we fixed that, but the issue was still there. And the problem was that they generated this plan shape that was very, very funny. So how many people remember in SQL 2005, we would always have these const table scans, nested loop joins whenever you had partition tables? Okay? We changed the way that we did partitioning from 2005 to 2008, partially to make it go faster and to work on how the optimizer generated plans so that it would do a better job. But in the 2005 timeframe, we had some special logic to add this const table plus apply. Or an apply is just another name for a nested loop join in our internal algebra. And it generated this weird shape. How many people have ever seen an update on the inner side of a nested loop join? Yeah, I have, but it's because I helped write this code. But the rest of you haven't, and it's not very common. But I saw this plan shape, and I thought to myself, well, that is odd, especially because what they were running wasn't supposed to be doing anything like this. We had a special optimization in the server because you're not allowed to do parallel updates to a single table. I'm sure most of you know this because yesterday you reminded me several times that we don't do parallel updates on a single table yet, which someday hopefully we will. But we have this workaround for partition tables. The restriction is actually that inside the storage engine you can't have more than one parallel thread running inside of each table. Storage engine table, not user table. So if you have a partition table, technically you could have one thread in each of those and you'd be just fine. To you, that's parallel, right? So we built that. And it's called a per partition update plan. So if you're doing updates that are all within a particular partition, then we can generate this plan shape and do all sorts of fancy stuff. We'll see if you guys can go generate a plan. Please mail me if you can generate this in the wild. I've never seen it in any real customer. But we built it anyway because we were being very aggressive one day, thinking that this would be awesome to do. And we checked it in, didn't tell our boss, and then I get called because this is slow. So the weird part is that we also are building an index spool over a fact table. The 8 terabyte table, index spool. Sound like a good idea? No. The actual part that's weird here is the 2008 version of the code, the new partitioning, and the old 2005 code started trying to talk to each other and they didn't like each other very much. So in this case, every single partition in the table would try to go and pull and build a big spool of the whole non-partition table, then pull out just the portion that it wanted for its partition and do some update to it, which I don't know what you guys would call it. To me, it's nonsense. So the problem that we had was that when I looked at the plan shape, I knew that I had a lot of rows coming in down at the bottom, and I should never, ever, ever have a case where the optimizer would pick an index spool. Because that's expensive, right? Reading and writing rows is not something that sounds very efficient, and we're not in the slow business. We're in the fast business. So technically, this tree didn't make any sense at all and was illegal. But the thing that I noticed about it was, just by figuring out where the index spool was, I knew that that was my big table, and I shouldn't have an index spool there. So I looked more deeply, and I couldn't run stats profile because the query didn't finish. But by looking at the plan shape, I was able to say, well, something's wrong here, and then we went and debugged it. Even if you don't end up debugging at the end of the day, since you don't have access to the source code, you can look at the plan shape and make that same conclusion. This was the wrong plan, and that's why it was running so slowly. Now let's talk about why we got this weird error after 8 hours, just to complete the example. How many people know what a uniqueifier is? For those of you who went to my talk yesterday, you do know. A uniqueifier is a special thing that we add to the end of a non-unique clustered index. And its job, as you might guess, is to make things unique. So if you go add a new row into that unclustered index, or sorry, clustered non-unique index, then there's no way that the system knows how to call it by its exact name so it doesn't talk to other rows. So we add this special token, and we will copy that token into other indexes, non-clustered indexes. And that way we can keep the whole system working properly. I think I lost my mic. Yeah, hello. I ran out of battery. Pardon me. Turn it off, please. Hello? Okay, now here we go. Excellent. So to complete the thought, we ended up with this 8 hours and then it errors. Now, uniqueifiers are nice in the sense that you don't have to actually make a unique row. We'll do all that work for you and keep it all up to date. And we have the ability to store up to 2 billion uniqueifier values. In this particular case, the table had 2.5 or so, 4.5 billion rows, more than 2 billion. So after 8 hours of processing 2 billion rows, it decided it didn't have any more uniqueifiers. Now, the funny part was this was a clustered unique index. Right? So why would it happen? And the answer is that index spools are tables underneath the covers. And we were creating an index on partition ID because we were confused. But partition IDs are non-unique. And as a result, we would add a uniqueifier implicitly and then run for 8 hours and then puke. Yeah. So the lesson here is not that you need to go understand how these kinds of plan shapes work. It's that ultimately I just had to guess what was wrong, right? There's no way I'm going to sit around for 8 hours in a debugger and watch this thing. And I couldn't anyway because it was a live system. So my only real option was to just take a look at it and say, well, what does the plan shape mean? And what should that do? And being able to read those query plans is effectively what I did to guess the right answer. Then I went and debugged and I found what exactly was wrong. But you can do the same guessing. And that's the time when you should call CSS, by the way. Don't attach the debugger and try to do this on your own. It'll hurt your head. Okay, I think this is my last example. I spent some time recently, some of you may know I work remotely for Microsoft. I used to live up here in Seattle, but I now live down in Texas, and I travel up here regularly. And the nice part about that is I get to see a lot of customers, and I talk to them in my regular work. And when I'm here, I get to sort of see what happens inside of Microsoft. So I get both worlds. And one week when I was flying back home to Texas, I was sent an email, and right before I got on an airplane, and the email was, oh gosh, the bug database is down. And Microsoft SQL Server runs on a bug database. Everything has to go through a bug database. If someone sneezes, there's an entry put in the bug database. If you want to run a test run, you have to put a row in the bug database. So it's not really just the bug database. It's the thing that makes SQL Server run, right? And if it's down, we have 1,000+ people who are not doing work. Another bad day. So just to make sure that you guys understand, I don't actually run the bug database, but I managed to sweet talk my way into having SA access on the bug database because I was tired of queries being slow one day. And therefore, I became the administrator when the actual administrator had twins and was just out. So they sent me mail, and I was using the glory of in-flight internet to try to debug our live system on the way home. And doing things that you should not do to live systems unless you are reasonably sure that you know what you're doing or you're willing to bet like me. So it turned out that all the systems were running slowly and things were timing out, and all the requests you would just click go in the bug database and you would never actually get anything back, right? And users love that, don't they? Right? My UI is non-responsive, please do something. And it turned out they had just done an upgrade of our bug database backend software, and it also turned out that they happened to have moved hardware, although I didn't know that at the time. Now, the new hardware was really cool, but the system was dog slow. So first thing I did was go look at sysprocesses. Now, there's a more recent up-to-date version of the DMV that you can use, but this was the one that I could type at 30,000 feet most efficiently. And I saw that resource semaphore, resource semaphore, resource semaphore. And that typically means that some things are blocking, waiting on something. It could be memory, it could be CPU. In our cases, it was CPUs. So OLTP systems typically shouldn't have this problem because all the queries should be really small and they should finish in less than a second. We happen to have a bug database where you can do all the bug operations and people do custom reports. So the custom reports are, I want to see all of the people who have too many bugs open on my team so that I can go tell them that they have to go fix their bugs, for example. And so this is a bad situation. You don't want the reporting workload on the same system to be stomping on your OLTP workload. So my guess was reports were the problem, because in the past we've seen that. So the next thing I did was go look at memory grants. And sure enough, I saw that there were a bunch of queries that were DOP1. I need to zoom in. Hold on, let me figure out how to get another hand. Okay, so you'll see here that we have some queries that are running DOP1, and there's a couple here running DOP16. Well, I can tell you I don't love any report query DOP16, right? But for whatever reason, it's running that way. And you'll see here requested memory, it's 1 gigabyte. I mean, the box doesn't have that much memory at the end of the day, right? It has maybe 2 gigabytes of memory or 4 gigabytes of memory or something. But you shouldn't be using 1 gigabyte of memory for a stupid report query. So they can wait for their report query. I was very tired. It was the end of the week, flying home. I didn't want report queries to be ruining my flight. Okay. So first things I did was say, well, I don't know what's going on here. So I just killed those guys and set the max DOP on the server to 4. And the reason is that I could go set up resource governor. Boris told me later you should have gone to set up resource governor, since of course he wrote that. But I'm like, I don't remember how resource governor works. And I don't want to do that. I just want max DOP 4. So no query should use more than 4 DOP anyway, so let's just do that. And that worked out okay, right? At least I got that down. So that cut down the memory requests, and it cut down the number of DOP problems that I had. It was still slow. I'm like, oh, that sucks. Okay, what else is wrong? So I started looking at individual query plans. And we actually had deployed a whole pile of custom indexes on this so that the reporting workloads wouldn't have as much random I/O. And we're willing to pay the disk space, and we're even willing to allow updates to be slow because, frankly, on the size of our bug database, they were already slow. So just a little bit more slow didn't matter that much. So I created about 30 or 40 indexes on the live system while I was flying home at 30,000 feet. And the thing I wanted to show you was the pattern that I used. So you'll see here that the same table has a couple of different references to it. And I saw this on every single query plan. And one of the dirty little secrets is that the guys who wrote the bug database software needed to do a slightly better job on indexing, which I've communicated to them, but they have not fixed yet. But overall, in this particular case, I had permission to add indexes because we're all one big happy Microsoft family. And I'm the one that tells them what indexes to create anyway. So the thing that was important here was that if you see these patterns where you're joining lots of different indexes from the same table, that's often a case where you don't have covering indexes on a table. Now, that doesn't mean you should automatically go make everything covering, but in my particular case, I knew that one of the reasons why the system was so slow was it gets overloaded on I/O or it gets overloaded doing hash joins to try to put all these things together. So in order to cut down the number of hash joins, I would go create covering indexes and say, well, I'm willing to make updates a little bit slower so I have fewer hash joins and make the system run faster. It's a balance, and it's not something that I recommend that anyone here do on a live system unless you are really, really brave. But the pattern is the right pattern, and you can then go through a testing situation to figure out what's the right set of indexes. We use the missing index DMVs to figure out what those were. The missing index DMVs are imperfect, but they're usually a pretty good 85% approximation of what's wrong with your system. So I run this particular query, and we'll post the slide deck on my blog, and it'll be part of the conference thing as well. But basically, this goes and joins a couple of the missing index DMVs together. And give me a second to zoom in so you guys can see it. You don't need to write down this query, but it's basically joining various missing index DMVs together to look for common cases of indexes that are not there in lots of different queries in the system. And if we find cases that are not there where the optimizer thinks, wouldn't it be nice if I had this index? Often, especially if it's a really, really big number in terms of what the overall advantage would have been, it's usually a pretty good indicator of where you could have used an index. So it might not get you to an optimal index set, but it probably will get you 85% of the way there. So this I run on lots of systems because usually people don't optimize them, and then I can look really good when I go run this and fix their stuff in an hour.
When you created these covering indexes, did you get rid of the other indexes that you saw that it was joining to itself?
Did I get rid of the other indexes when I went and did all my magic? No, I wasn't that brave. No, I should clarify that I knew from prior experience, since I worked on this system before, that adding indexes was acceptable. And the indexes that were part of the existing system I didn't want to take away because it might cause the app to break. So I just said, fine, I'll add indexes. And that can speed things up. And that's so the question I asked next was, well, why were the indexes not there? Because I had already created all these indexes before, and they were gone. And the answer was they moved all the hardware. And the actual migration to the next version of the software didn't copy all the indexes, right? Well, that sucked, right? That was 2 hours of my flight. where I could have been sleeping. And then I fixed all that, and it was still slow. Yeah, welcome to my world. So the next thing I learned was that as part of the process of copying all this stuff over, there was actually another guy who independently of me had gone and done a special optimization on the server as well. And we have a lot of custom columns that are added to the schema in this particular database, and most of them are mostly null. So there's 500 columns that are mostly null. And they had gone and deployed sparse columns. How many people know what sparse columns is? It's a new storage engine mechanism in 2008. And it can basically reduce the width of your row, which means fewer database pages, which means fewer rows to scan and fewer pages to scan into memory. In this particular case, we were doing 3 times as many pages without having it. And therefore, all the report queries were taking at least 3 times longer. And actually, because we had bad plan choices as well, they were taking more than 3 times longer. So we actually had some which would usually run in 5 minutes, and they were running in 2 days. I let one finish. So this boiled down to a lot of space that we could save. And we're actually still in the process of trying to deploy this because there's no online way to turn off, to add sparse columns to a table. Because we're still running, right? We can't stop the bug database system. And we don't have an online add sparse column command. So I spend a lot of my Sunday mornings actually working on the bug database. Yes, I see. I'll be done in a second. So takeaways. Stats profile. Understand what kinds of things your system does, if it's an OLTP system or a data warehouse system. And if you know those things, then you can guess what kind of query you should have and what they should be doing. In my particular case in the bug system, I knew that the OLTP workload was far more important than the reporting workload. It's not that I want the reports to suck, but I know what's the priority order of queries in my system. And that tells me what kinds of solutions I can deploy whenever the proverbial excrement hits the proverbial fan, which seems to happen very frequently in my life. So I think that if you have these same tips and techniques and you do the baselining that Boris told you about, then you'll know what's your playbook for the next time something goes wrong. And maybe you can't predict all of them, but I can assure you that being prepared is far, far better than just trying to figure it out after the fact. Often I get thrown in and there's nothing, right? I have to fix a system that's literally broken and people are losing millions of dollars an hour. This is not a good situation, and as a DBA, you don't want to do that. Instead, figure out how you can prepare for that. Make it a little bit easier on yourself. Use the techniques that we have and let us know how they go. We have blog entries and we can write white papers on areas if you think there's things that we can help you with. Do we have any more slides? Are we done? So we have a thing here that just is a summary of the tools that we used in the presentation. So we'll post this up so you can see. And I think that is our last slide. Here's some stuff you can go read as well. And I have a blog at the bottom called Connor vs. SQL. And I answer questions there. So if you have things that you want to know, let us know. Okay, thank you very much, everyone.